In this video, we're going to focus on curve arrow notation, also known as electron push-in arrows. Now, whenever you see a full arrow, this represents the flow of two electrons, or an electron pair. If you see a half arrow, it represents the flow of one electron. Typically, you'll see that when dealing with radical reactions. So let's go over a common acid-base reaction. So here we have acetic acid, and we're going to react it with hydroxide. And let's put the lone pairs on each oxygen atom. So what's going to be the products in this reaction, and how can we show the mechanism using curved arrow notation? We know that acetic acid is a weak acid, hydroxide is a strong base. So hydroxide is going to abstract a proton from the acid. Acids are proton donors. Bases, they're proton acceptors. So we know we're going to get water as a product, and we're going to get the conjugate base of acetic acid, which is acetate. How can we show arrows that will help us to get the products that we see here on the right? Now, when drawing the arrows, you want to draw the arrow from the nucleophile to the electrophile. The nucleophile is typically the base, generally speaking. It is the molecule that is electron rich. The electrophile is typically the acid, and it's usually electron deficient or electron poor. So when drawing the arrows, electrons will flow from a region of high electron density to a region of low electron density. In other words, it usually goes from a nucleophile to the electrophile. So we could say that the electron density around an oxygen is pretty high because it has a negative charge. This hydrogen is partially positive. This oxygen is partially negative. Whenever you have an OH bond, because oxygen is more electronegative than hydrogen, it's going to bear the negative partial charge. So this hydroxide ion is attracted to the partially positive hydrogen. So we're going to draw the arrow from the oxygen to the hydrogen. Now think about what's happening here. This arrow tells us that the oxygen is going to use two of its electrons, or one lone pair, to form a bond between itself and hydrogen. So those two electrons are right here in this sigma bond. They were used to connect the hydrogen and the oxygen bond. Now, this bond broke right here, the OH bond. Where did those electrons go? Did they go to the hydrogen or to the oxygen? Looking at our products, we can see that here the oxygen had two lone pairs. Now it has three. So we can tell that the electrons in that bond went back to the oxygen atom. And so we're going to show the flow of those electrons with this arrow. So it's going to point towards the oxygen atom. And so really, that's how you can use the curve arrow notation. Remember, it represents the flow of electrons, where the electrons are going, how they're being used to either break a bond or form a bond. And that's what we have here. So those are the only two arrows that we need to show the progression of this reaction. Let's look at another example. So here we have Br2, and we're going to irradiate it with radiation, let's say UV radiation, and something's going to happen here. When you irradiate a halogen like bromine, iodine, or even chlorine, the bond that connects these two atoms can break. When that bond breaks, where will the electrons go? Will they go to the bromine on the left or the bromine on the right? So once this absorbs UV radiation, that bond will break. Now, both of the bromine atoms, they're equal. They're equal in electronegativity, so their ability to pull electrons to themselves are exactly equal. Therefore, when that bond breaks, one electron is going to go to the bromine on the left, and the other is going to go to the bromine on the right because they both have an equal pull on those two electrons. So in this case, we'd use half arrows because there are two electrons in that bond. One is going to the left, one is going to the right. So remember, a full arrow represents the flow of two electrons, but a half arrow represents the flow of one electron. So we're going to get two separated bromine atoms with an odd number of electrons. Whenever you have an atom with an odd number of electrons, that's a radical. So this type of reaction you'll see when going over radical reactions. This type of bond cleavage is known as a homolytic bond cleavage. The prefix homo means the same. Each atom gets the same amount of electrons. And lytic means, to split apart, think of the word lysis. You're splitting something down in the middle. So we're breaking the bond evenly, and those two electrons are being shared equally, or being taken equally among those two atoms. Now let's look at a heterolytic bond cleavage. So let's say the carbon-bromine bond is about to break. Where will the electrons go? Will they go to the carbon atom or to the bromine atom? Carbon has an electronegativity value of 2.5 on a 4.0 Pauling scale, and bromine, the electronegativity is 2.8. So because bromine is more electronegative than carbon, when that carbon-bromine bond breaks, bromine is going to have a stronger pull on those electrons. So the full arrow is going to go towards bromine. And what we're going to get is a carbocation with an empty p orbital, and we're going to get a bromide ion with 8 electrons, or rather 8 valence electrons. So that is an example of a heterolytic bond cleavage. The prefix hetero means different. So carbon didn't get any electrons when that bond broke. Bromine got both of the electrons. Now let's look at another situation. Let's say if we want to break the carbon-hydrogen bond. How should we draw the arrows? How should we show it using curved arrow notation? Now carbon is more electronegative than hydrogen. In the previous example, carbon was less electronegative, so it had the partial positive charge. Bromine was more electronegative, so it had the partial negative charge. Now for the carbon-hydrogen bond, the situation is different. Carbon is more electronegative, so it's going to bear the partial negative charge. Hydrogen is more positive. It's less electronegative, more electropositive, so it's going to have the partial positive charge. When that bond breaks, the electrons are going to go towards the more electronegative carbon atom. It has a stronger pull on the electrons in that bond. So in this situation, we're going to get a carb anion rather than a carbocation. So that's another example of a heterolytic bond cleavage. Now for those of you who are studying for the first exam of organic chemistry, I have a practice test that can help you with that, and it's posted in the links in the description section below. Now for those of you who want access to the free version, which is a little bit shorter, if you go to YouTube and type in the search box Organic Chemistry Exam 1, the free version should show up, but the full version is going to be in the description section below for those of you who are interested. But now let's get back to this video. Now let's consider the reaction between hydroxide and methyl bromide. What do you think is going to happen in this reaction? Feel free to show the arrows that will help us determine what the products of this reaction will be. Hydroxide in this reaction is going to behave as a nucleophile. When hydroxide abstracts a proton, it's behaving as a base. When it attacks a carbon, it's behaving as a nucleophile. The bromine is partially negative. Carbon is partially positive with respect to bromine. So hydroxide is going to be attracted to the nucleus of the carbon atom. And that makes it nucleophilic. It makes the carbon atom electrophilic. So we're going to draw the arrow from a region of high electron density to a region of low electron density. So we could say hydroxide has a lot of electrons. It has a negative charge. The carbon with the partial positive charge, that's a region of low electron density. So the arrow is going to flow from hydroxide to carbon. And what's going to happen is we're going to take 2 electrons from hydroxide and use that to form a bond between the oxygen and the carbon atom. So here is hydroxide, now it's attached to carbon, and we still have the other hydrogen atoms attached to it. Now carbon can only form 4 bonds. So evidently this bond has to break. And that's what's going to happen. When this bond breaks, we know the electrons are going to go towards the more electronegative bromine atom. And so we're going to get bromide as one of the products. So that's how we can represent this reaction using curve arrow notation. Now here we have 2,4-pentadione, and this particular diketone, it's a beta diketone, has an acidic alpha hydrogen. The hydrogen that's on a carbon, which is adjacent to a carbonyl group, that hydrogen is relatively acidic. And when it's between 2 carbonyl groups, the pKa for this hydrogen is 9. The pKa for a hydrogen that's next to 1 carbonyl group, that's around, it could be anywhere between 17 and 20. So like for aldehydes, it's 17. For ketones, it's like close to 19, but somewhere in this ballpark range. So this is the most acidic hydrogen that's on this compound. So hydroxide, rather than being a nucleophile attacking a carbon, it can act as a base and go for the hydrogen. And that's what's going to happen in this example. Now, we know that carbon is more negative than hydrogen. So carbon is partially negative with respect to this hydrogen, and that hydrogen is partially positive. So hydroxide is going to be attracted to it. So we're going to draw the arrow from a region of high electron density, that is from the nucleophile, to a region of low electron density, that is the electrophile. So it's going to go from hydroxide to the hydrogen. So what's going to happen is we're going to use a lone pair to form a bond between oxygen and hydrogen. And so we're going to get water as one product. We have 3 lone pairs on oxygen. We use 1 to form a bond, so now we're left with 2. Now what happens when the carbon-hydrogen bond breaks? If we take away the hydrogen, that bond has to break. Where will the electrons go? Because carbon is more electronegative than hydrogen, we know that when the CH bond breaks, the electrons will go towards the carbon atom. And so we're going to get a carbanion. Now the reason why this hydrogen is so relatively acidic for a CH hydrogen is because this carbon with a negative charge, it's part of a resonance system. The negative charge can delocalize into the carbonyl group and it can be placed on an oxygen atom. And the situation is more stable if we put the negative charge on the oxygen atom rather than the carbon atom. Because oxygen is more electronegative, it can better handle the negative charge. So let's draw the resonance structure. Now this carbon that's part of the carbonyl system, it's partially positive because it's attached to an electronegative oxygen atom, which is partially negative. So when drawing the arrows, we're going to draw it from a region of high electron density to a region of low electron density. So the arrow is going to flow from the negative charge towards the carbonyl carbon. So what's going to happen is it's going to be used to form a pi bond, and then this pi bond is going to break. Those electrons are going to go on the oxygen atom. And so this is one resonance structure that we can draw. So now we have a pi bond here, and we have 3 lone pairs on the oxygen. Now keep in mind, we can also move the negative charge here and put the negative charge on the oxygen on the right. So, but that resonance structure with this one highlighted in blue, they're equivalent. So we can draw a total of 3 resonance structures for that particular ion. Go ahead and try these two. Use curve arrow notation to draw the resonance structure of each example. By the way, for those of you who want more examples on resonance structures, I'm going to post the full video in the in the description section below this video. But if you want the free version, if you go to the YouTube search bar and type in resonance structures organic chemistry tutor, it should come up. So let's start with the first example. How should we show the arrows to draw the resonance structure for this allylic carbocation? Now it really helps to identify the region of high electron density with the region of low electron density. The region of low electron density is going to be that empty p orbital on the carbon with the plus charge. So that is the electrophilic center. The nucleophilic center has to do with the double bond. That's a region of high electron density because we got 2 pi electrons that can move into that empty p orbital. And that's what's going to happen. So we're going to take these 2 electrons and move it here. As we do so, we now have a pi bond between those 2 carbon atoms, but this carbon lost a bond, so now it's going to be electron deficient, which means it carries the positive charge. Notice that these 2 resonance structures are equivalent. If we want to draw the resonance hybrid, it's going to look something like this. Because the double bond is between these 3 carbon atoms, we're going to have a dashed line between those 3 carbon atoms. Now the plus charge is shared among those 2 carbon atoms, so we can put a partially positive charge on those 2 carbon atoms. Because they're the same, we can quantify and say it's going to be half of a charge on each of those 2 carbon atoms. But this is a good generic answer when dealing with these types of questions. Now let's move on to the next example. How would you use curve arrow notation to show the progression of, to show the formation of the resonance structure for that ion? Now, which one has higher electron density? Would you say the double bond or the lone pair with the negative charge? The double bond is neutral. The lone pair has a negative charge, so it's more nucleophilic. It's more negative. So in this case, the double bond is going to be the electrophile. Here, the double bond's neutral. The plus charge is positive. So neutral is more nucleophilic than a carbon with a plus charge. So this time, the arrow is going to flow towards the double bond rather than away from it. So it's going to flow from a region of high electron density towards a region of low electron density. So the first arrow, what we're going to do here is we're going to take this lone pair, use it to form a pi bond, and then we're going to break this pi bond, move those two electrons to form a lone pair on the other carbon atom. So we're going to have a pi bond here, and here's the negative charge. So those two structures are also equivalent, and if we want to draw the resonance hybrid, it's going to look very similar to the situation above. The double bond can move anywhere between these three carbon atoms, so we're going to use dashed lines to represent that. And the negative charge is shared among those two carbon atoms. So that's basically it for this video. So now you know how to use curve arrow notation to not only predict products but also to show the progression of a chemical reaction, and you know how to use it to draw resonance structures as well. Now, for those of you who want to access my extended organic chemistry videos, you can access it at my Patreon membership program at patreon.com/mathsciencetutor, or in my YouTube membership program, which you can join in the video below. Now, if we click on this organic chemistry post, it'll show you all my full-length organic chemistry videos. So I have this video on pKa values for those of you who are studying acids and bases. For those of you who are just studying organic chemistry, this basic introduction video will really help you get started. And I have some other videos as well: hybridization, resonance structures. The free version of this video is about 20 minutes long on YouTube, but the full-length version is about an hour long. Acids and bases, functional groups, Newton projections. The worksheet contains all of the problems in the full-length video. Some of you have asked for worksheets. You prefer to work through the problems that way instead of watching a long video. So I have it for not all of my videos, but some of them. So we have chair confirmations. Now, for my organic chemistry exam 1 video, you may have to type it in the search box to get it. Or if you look at the description section of the referring video, it'll take you directly to that link. But here is the worksheet. Now, if you want to watch a 7-hour video, you can do it that way, but if you prefer to print out the worksheet and work through the problems that way, you could do that as well. By the way, post a comment in below this video. I want to know what your thoughts are. Do you prefer to watch the 7-hour video, or do you prefer to study for the exam by getting a printout of the worksheet and working through the problems while you're in school? Let me know in the comment section below. Now, I have other videos: stereochemistry, specific rotation, SN1, SN2 reactions. There's a practice test on that, 77 practice problems. So here's the video with the practice test, but I haven't done the worksheet yet. We got alkene reactions, alkyne reactions, alcohol reactions, radical reactions, and then my organic chemistry 1 final exam review video. So the video is actually finished, but the worksheet is coming soon. So let me know, for those of you who are actually interested in getting these worksheets, do you prefer to watch a 6-hour final exam review video, or do you prefer to have a printout of the 100 practice problems and work through it at school? Let me know in the comment section below.